Hey chemistry students, Mr. Hunter and I are here today to introduce Unit 11. We're going to look at solutions, and the first lesson is the introduction to solutions and their properties.
The first objective is to define and describe the composition of solutions.
We want you to explain differences among colloids, solution, and suspensions and be able to give an example of each.
Define and describe how solutions form.
We want you to define solvation and hydration.
And lastly, compare properties of electrolytes and non-electrolytes in solutions.
All right, this is a lot to cover, so we better get to it.
Alright, so first of all, we have to go back and do a slight review of our solutions. The first term is a solution itself, which is a homogeneous mixture of two or more pure substances.
Okay, so solutions have two components. They have a solvent, and the solvent is the substance that's generally present in the largest amount, and it's the substance in which the particles of the other material are evenly dispersed.
And then the next word is a solute. This is the substance that is dispersed in the solvent. So think salt in water. The salt would be your solute, the water would be the solvent.
Now, most often the solvent is a liquid. So just about all the solutions that we deal with in chemistry have a liquid solvent, and most often that liquid is water, but it doesn't have to be that way. Gases, solids can also be solvents as well.
Okay. So there are several types of solution types. There's a solid and solid. These are usually your metal alloys such as steel. And why you're saying steel is iron, it's actually iron and carbon.
Right. And you can have a gas dissolved in solid. Hydrogen gas actually dissolves quite well in some solid metals. The atoms are small enough that they can fit into the crystal lattice of the metals, and it's dissolved.
All right. Next is.
By the way, while we're on that, this is how they talk about using hydrogen as a fuel for vehicles, and one of the things they want to do is try to make the fuel tank maybe out of metal particles like palladium, and then the palladium can actually kind of dissolve the hydrogen and hold that hydrogen so the hydrogen tank is less flammable. I was just reading about that the other night.
The next is a liquid and a solid. This would be hexanes dissolve in paraffin wax or something like that.
Okay, you can have a solid dissolving in a gas, and you might not know about these, but your parents or grandparents do moth crystals or mothballs. They are moth crystals and mothballs are a solid chemical. It's often paradichlorobenzene, and it actually sublimates into the air. So it goes into solution with the air at room temperature slowly, and I guess it repels moths so they don't eat your wool clothing and things like that.
Next would be a liquid and a gas. Think water evaporated into gas phase.
And of course, a gas can dissolve in a gas really easily. Air is a mixture of a number of different gases, and I guess you'd say that nitrogen's the solvent because that's the
70%.
70-some% of the air.
Okay. So there's another group of solutions, so to say. I mean, they're not quite solutions, but they're similar in certain properties. There's things called colloids, and colloids are slightly larger particles that are dispersed in a solvent, and they can be seen if you pass a light through them. They will scatter, and it'll look cloudy. This is called the Tyndall.
Tyndall, yep, the Tyndall effect.
And this it's still a homogeneous, basically a solution, but they're called a colloidal suspension.
Okay, so this one on the right is the colloidal suspension. The one on the left would be a solution, and you can see this one's not scattering the light. It's passing right through, but the light is hitting the slightly larger particles in the colloidal suspension and scattering off in other directions.
All right, and the next type is suspensions. These are even larger particles dispersed in a solvent. They also scatter light like colloids, and they do settle upon standing. So these are considered a heterogeneous mixture.
They're heterogeneous, and while the colloids would be lumped in with the homogeneous mixtures as well. So particle size, just for your information, a true solution is going to have particles that are on the order of 10 to the minus 7 centimeters or smaller. If the particles are slightly larger, say between 10 to the minus 5 and 10 to the minus 7, that gives you a colloidal suspension. And then larger particles yet are your suspensions.
Yep.
All right, just so you have some frame of reference, these colloidal materials that aren't quite a solution, they have particles slightly larger, there's lots of them. So, if we think of a liquid solute, which is what we're kind of most familiar with, paint, milk of magnesia, these have solid materials dissolved in liquids. Actually, I'm sorry, they're solid. These are considered solid solvents with liquid solutes. Paint would be, I guess, because there's so many pigments, there's more ground up solids. If we go liquid and liquid, milk, mayonnaise, face creams, hand cream, these never settle. The particles are large enough that they're considered colloids. Then you can even have gaseous solvents, whipped cream, shaving cream, those kind of foamy materials are also considered colloids. Solid, another one would be a marshmallow, gaseous solvent with a solid solute. Okay, we can have virus particles in the air are considered a colloid. So they're around us in a lot of places.
All right. All right, so our next thing to talk about is talk about how liquids interact with each other. We've talked about things back a while ago about polar solvents, nonpolar solvents, polar molecules, nonpolar molecules, and now we're coming back to that.
Right, so when we go to put two liquids together, generally one of two things happens. Some of these pairs of liquids are going to be miscible.
Yep.
Means they readily mix. So here's acetone and water. And when you put them together, it just looks like one liquid. They disperse throughout one another, and you can't really, you don't see acetone or water just as a liquid. It's homogeneous. Okay, but some of them we put together are going to have a layering, with the less dense one on the top, the more dense one on the bottom. Even if you stir them up, a lot of times they're just going to separate right back out. These are liquids that we would describe as immiscible. They just simply won't mix, oil and water. Okay, so the explanation, we've already covered this, but the miscible liquids are going to have molecules with similar polarities. So like mixes with like.
Your polar and your polar, or your nonpolar with your nonpolar.
So acetone's a fairly polar molecule. It's got some lone pairs on an oxygen sticking out. We know water is highly polar. They mix right together. Water and this molecule are immiscible because they have probably, this is a non-polar molecule. They're not going to interact. So they actually have a repulsion for one another rather than any kind of hydrogen bonding or attractions. So they don't want to mingle with one another.
Okay. So a quick review on what polarity is. There are some molecules that are polar, and they have a charge imbalance called a dipole due to the difference in electronegativities of their atoms and a lack of symmetry. This is an important factor in solubility. If you recall, there was a thing we taught you called SNAP. This is a terrible way to write SNAP, but SNAP is your symmetrical, nonpolar, asymmetrical, polar. So that is one way to determine if your molecules are going to be polar or nonpolar.
Okay, so bent molecules that have lone pairs sticking out on one side on an oxygen or something, and hydrogen on the other side, or some other thing without the lone pairs, they're going to be polar. Okay, polar dissolves polar. Nonpolar will dissolve other nonpolars. So, and it kind of breaks down like this on this chart. So even though we consider like ionic a whole separate class of bonding, okay, but the thing about ions is they're charged, and polar molecules are charged, so they're just not fully charged like an ion is. But a polar molecule has ends which are, more positive on this end, more negative on this end.
Yep.
So polar solvents will interact with that, and we're going to look at that on the next slide. The ion is just overall either positive or overall either negative, but polar solvents will interact with anything that's got charge on it in some way, where the nonpolars don't interact with charge. So nonpolar keeps to itself, and basically anything that's polar and anything that's ionic, they're going to tend to be compatible in solutions.
Yeah, and that comes back to our like dissolves like, polar dissolves polar ionic, and nonpolar dissolves other nonpolar. So that's kind of the rules for how you would expect molecules to dissolve or be soluble
At
in
least
one another.
the general rules. There's lots more specific rules in this, things, what that's for AP chemistry.
Yeah. So we're going to talk about polar solvents first, and water is the most important because that is the most abundant and most common solvent that we as humans are used to dealing with. So for these to happen, we dissolve a polar and ionic substances by a process known as solvation. And on the right-hand side of this slide, you'll see these little positive, negative things, and this big chunk down here. This big chunk down here could be sodium chloride, and the water up here is starting to dissolve it by solvation. So let's put a circle.
What do we mean by solvation? We actually mean that each ion gets surrounded by its own little team of water molecules. And actually, this would be three-dimensional. They would be on all sides of it, more like a sphere than a square, kind of the way it's drawn there. But the water being polar has charged ends. So the positive end of the water molecule, where the hydrogens are, is going to orient towards this chloride ion because the chloride's negative and the opposites are attracting. So we call that a hydration shell or a hydration sphere. We're going to see that around any ion that is dissolved. In fact, the water kind of acts like little wedges and kind of wedges in there and pries these ions apart from one another. And then the ions can't get back together because they've got all these shell of water molecules around them that won't allow the cations and anions to get back together. I think we have a
Yeah, we have a
cation
positive
down
here
there.
too.
All right. So now, what do you notice about this one that's different? This would be your sodium ion.
Yeah. So in this case, the sodium now is positive, and the water, since it's polar, has its negative end, or the oxygen, pointing in there, and it's forming a sphere around this sodium, and also having a hydration shell or hydration sphere around this sodium. So the positive and the negative are interacting on this one as well. And then lastly, we now know about ionic things, but there are also polar molecules that are not ionic. So if you see here, polar solutes, things like, in this case, I think we're doing with ammonia. You can see ammonia drawn here. You can see water drawn here. You can see water interacts with itself, the positive end interacting with the negative end. Same with ammonia. Ammonia's over here. The hydrogen's interacting with the nitrogen. These are actually the hydrogen bonds, at least for water. And actually, ammonia also has hydrogen bonds. So when these two molecules are mixed together,
they can just hydrogen bond with each other.
And they're miscible in all amounts then. When they have similar type bonding properties, they will be miscible with each other. So you can just see they're mixed together now, and they're just interacting the positive end and the negative end in each molecule with each other.
Now for something completely different, this is our comedy break for the video.
Yeah.
Help, help, I'm dissolving. But bears are insoluble. That's easy for you to say. You're not polar.
Yeah,
I get it.
Yeah, that's a good joke for the morning announcements. All right, so the last thing we're going to talk about are things called electrolytes and non-electrolytes. An electrolyte is anything that produces ions when dissolved in water. Examples: salts, acids, and bases.
Basically, ionic substances,
Yes.
or things that generate ions when they're dissolved.
Without electrolytes, things could not conduct current in water. So if you are sitting in pure water, you would not be electrocuted if someone were to put an electric current or try to put an electric current through it. The issue is we have a lot of salt in our body that likes to leak out into the water. So never try this at home, but pure water does not conduct.
And most of your tap water is not pure water.
Yeah.
It's got enough ions in there that you will be electrocuted.
So do not try this at home. Now the next type is a non-electrolyte. These are things that do not produce ions when dissolved in water. Examples: sugar. We've always had sugar water, and ethanol, and other types of molecular compounds that are soluble in water but don't conduct because they don't make ions.
And this is important in the medical field too, because you've probably heard that. That's a medical term, electrolytes. And when you are sick or ill, or sometimes you have an electrolyte imbalance, and they will carefully administer like an intravenous to you And sometimes you're getting just sugar water if you don't need the electrolytes, but sometimes you're getting water with ions dissolved in it because you need to replace maybe ions or your are imbalanced. And so part of your body's natural balance is to have the right amount of electrolytes in your blood, inside the cells of the body. And so that's an important medical consideration as well.
Alrighty. So the first PVQ is to draw the hydration shell of water molecules that would be around a fluoride ion.
Remember what charge a fluoride ion would have and draw the water molecules in the proper orientation around it. All right, number 2, a mystery liquid is immiscible with water. Make a prediction based on that observation about the nature of the mystery liquid.
Talking about either bond type, polarity, something along those lines. So,
what kind of substance might it be?
all right. Well, have a good night.